program. If you have any questions, please feel free to contact me. So what I'm going to tell you in this second part has two parts. First part, I will discuss about 5 or 6 very important recent issues. Because I have given you a background about aerosol, I hope you will be able to understand and follow. If you are not able to understand, please ask me questions. I will be able to explain more during the presentation or during lunch time or after the time. So the question is based on what I have said. The basic question we are trying to see why Indian climate change. There are global problems and there are problems relevant to Indian context. So I will be focusing on Indian climate problems and outstanding issues relevant to our country. Few of them. There are so many issues, but because of limitation of time, I won't be able to tell all of them. But this is the one thing we want to remember before I come to issues. If you see the black carbon concentration all over the world, developed countries are responsible for most of the carbon dioxide emissions, and developing countries are responsible for most of the black carbon emissions. So both are warming agents. CO2 is a warming agent, black carbon is also a warming agent. So if and the difference between the two is CO2 lifetime is hundreds of years and black carbon lifetime is about 20 days. I have shown you. You can also calculate it's about 20 days. So there is a relevance for this residence time also. I will tell you, but this you remember before I go to the issues. The issue 1. Build-up of aerosol in India. Indian Space Research Organization is maintaining a network of aerosol observatories all over India. It starts from Hanle in Himalayas to the Himalayas. From here it is Gujarat to Dibrugarh in east. So all over this place we have a gap here. And this whatever stations which are blinking, that is going to come very soon. It is not there right now. So if you take data from this network, it's called AEROSOL predictive modeling over India and for AFI. Bangalore is also part of this network. And you will see that what is shown here is black carbon concentration over the sites measured. And 35 surface observatories and highest black carbon mass concentration from the Indo. So that's one point you have to note. And you see the data from Air Pollution Control Board. You take it is available in the website, and it is 2010. And if you see different cities, you will see that the highest mass concentration is Kanpur, Kolkata, Delhi, Patna, and the site shown here. And you take any satellite data, you will see a thick band of aerosol here. And this threshold values are shown critical high, greater than 360 microgram per meter cube of air is very high. Permitted concentration for residential areas is less than 140 microgram. You can see that almost all cities in India are above threshold level for healthy atmospheric conditions. And some locations are very, very bad. Critical means it is not at all good for health. So, question is why Indo-Gangetic basin is polluted. Indo-Gangetic basin, there is a relevance because it is very close to Himalayas. So that is one important thing. Other than health, see the first thing is health of people living, plus its proximity to Himalayas is a major issue. I will tell you why it is polluted. Not because the emission is so high in that region. The reason because Mumbai, Chennai and all also should be very much polluted. But the reason it is slightly polluted is there are several reasons. 16 out of 23 major 1000 plus megawatt thermal power plants are located in the valley areas. Because hydroelectric projects are very less, because it is plain, you don't have a topography. And India coal has a very good ash at 24 to 45%. So thermal power plants are major responsible factors for high emission rate. Plus population density is high and most importantly topography. See, Himalayas are blocking the emissions. It is not permitting it to disperse. I told you in the last presentation that solution to pollution is dilution. So Himalayas are not permitting dilution here. And see this side here again elevated. This is digital elevation index. The altitude structure is shown here. See here also you have elevated land and here it is Himalayas. So it is something like a canal, a small canal. So the entire pollution is confined between the two. So there is no escape for the emitted pollutants. That is not the case with Mumbai or Chennai or Calcutta. Here, all these emitted will escape to ocean and land sea circulation is there to dilute it. Plus, there is nothing to block. And I said build-up of aerosol over the Indian region. If you take all India average aerosol optical depth, you will see that there is an increase of 2.4% per year of aerosol optical depth from 1984 to 2012. So this is the all India average, and this is annual mean, and this is all India average. And if you extrapolate this change, you will see that by 2048, aerosol optical depth will be double. It approaches mean, and currently it is about 0.5. That would double and approach mean. So 2040, 2050 scenario, if you take, it is going to be very high. Aerosol optical depth is defined with this equation. So surface is within direct solar radiation. If you calculate I is equal to I squared potential minus tau or an overhead sun, that means tau is equal to 1. That means I squared by E. So there is an exponential reduction in the surface touching solar radiation. That is what is indicated. And that scenario is not going to be very good. This is the black carbon concentration, and this is the total aerosol concentration. So if you see the global scenario, see NASA is maintaining a station across the globe. It is called AEROSOL, and many stations are there. India also few stations are there. And if you take data from the stations, and there is RFI over India, AeroCan over Canada, Photos, France and Africa, Skynet in Japan. To take data from all these stations, this is what you will see. In most of the stations, you have a decreasing trend in aerosol, but over India and part of China and Africa, you still have an increasing trend in aerosol. So build-up of aerosol over Indian region is one issue which is bothering us. And 73 sites, if you take, while more than 70% of science show increasing trend in aerosol, it is actually short and increasing. And it is not surprising. We are not surprised by this because you have growing cities and ever increasing urban population and traffic and rapid and unplanned industrialization. These are all leading to this situation. And if you see the increase, it was 1970, 2 million number of registered fields in India in thousands. 2 million in 1970, 2007 it was greater than 100 million, by 2015 it is going to be 200 million. So that is the way without any control, number of registered vehicles in India is going up. And if this happens, this is 2000 scenario, your surface solar dimming is 14%, and atmospheric warming is about 0.5 Kelvin per day. And you yourself can calculate this in the today afternoon, because you will be able to calculate by your own how much warming and how much reduction of radiation is occurring in the atmosphere. And if you estimate predicted 2050 scenario by extrapolating the optical method to 2050, you will see that surface solar dimming is 32%, and almost 1/3 of the radiation is going to be blocked on an all-India basis. So it is not going to be very small. Also, note that this 0.5 Kelvin per day is a daily mean. This includes day and night. So only daytime condition if you take, you have morning to evening. This 0.5 is average of morning to evening, not noontime conditions. Noontime condition will be, I can tell you, approximately 3 times larger than double of this. So you take multiply by 2, then you will get only daytime condition. That will be 1 Kelvin and 3 Kelvin per day. That will be the difference you have to do. So this 1.4 Kelvin, you need it to take 3 into 3, 9 Kelvin per day. It will convert it to a local noon conditions. And that is all India average. So local to local can be even higher. So few degrees Celsius increasing the temperature is not very simple. It is very, very high. So, and that also indicates that aerosol loading would be nearly double. Health issues in 2050 and depletion of direct solar radiation at the surface would be about 70%. So I don't have to worry. You people will have to worry. So you have to think about that. 2050 is far away from you. And issue 2, Earth radiation budget. See, it is often when we calculate the Earth radiation budget, we make measurements which you will see in the afternoon lab session, and then incorporate in radiation models. So then measured radiation budget should be able to simulate the radiation simulated by model should be able to compare with the measured ones. So if it is not agreeing, that means you are missing some energy somewhere. You don't know where. That is another issue. So if you take over Indian region, you see that this is one experiment we have conducted long back, and we have examined the effect of aerosol on radiation over Republic of Maldives. You can see that complete set of instruments were used, and we tried to answer the question: can atmospheric chemistry measurements explain the radiation budget? So if you use all the available information and calculate the optical properties which you will be doing today afternoon, and then you will make a model and use an RT model to calculate it and go to climate model, and then whether you will be able to simulate the measured radiation or not. That is what it will be. And this is one thing you should remember before I proceed. Once aerosol is formed, it can be existing independently, or it can go in a mixed state. So here, every aerosol species is existing independently, that is for external use, and here it can form complex structures from different sources. One can be as a core, and another aerosol can stick over that and form a shell over that. If you have a large particle and a large number of small particles, all the small aerosol can stick over this particle to form a layer over the particle. So the point you have to remember is aerosol radiative effect in this condition and this condition are entirely different. It is not same. What we measure is like this. We can't measure this because we are using a strictly chemical analysis, so only this you can measure. We cannot, even if you sample this kind of condition, it will be separated during the analysis. So there are several competing hypotheses about this missing energy. Why we miss energy over Indian region? There are reports over other region also, but I am talking about only Indian conditions. See, an unidentified absorbing species 50% in that. One group of scientists are thinking that we don't know a species which is present, not a discovery. It is present in the atmosphere. It is called gas X. Whether it is a gas or particles, nobody knows. And another hypothesis is that current estimates of aerosol black carbon, because it is absorbing, that can explain the missing energy, need to be multiplied by 4. If you want to agree measurements with model simulation, you need the absorption multiplied by 4. That is a huge number. If it was 1.1 or 1.2, that correction factor is something which I could accept. But something multiplied by 4 means we don't know about that. It is unacceptable, unacceptably large. So this is the current scenario. And one possibility is that inadequate description of state of things. So if you want to see anybody is doing research on this topic and more information, you go to these publications and you get the details. And one possibility is inadequate description of state of things. And that means estimates of aerosol climate impact assessment in the past so far are unrealistic and represent only lower bound. Actual impact is substantially larger than predicted by model. That means already we have a long list of climate impacts I have shown you in the previous presentation. That itself is an underestimate. That is what it indicates. Actual impact is even larger as on current scenario. So you can imagine what would be 2050 scenario in that case. And few words about black carbon. See, in addition to accepting its own impact, black carbon can substantially contaminate other aerosols. The reason is black carbon is so small. It is so small, it can get deposited over other aerosol, large aerosol like dust. It can easily deposit over that. Then when black carbon is depositing over dust, you just imagine it is large number of small particles which may not have much optical effect because its extinction coefficient is small. Because when particle is very small compared to the wavelength, its effect is not that significant. But then this particle is sticked on a large particle like dust. It will act as a dust is non-absorbing, slightly absorbing but not that absorbing. So it makes the dust a large absorbing particles. So its climate impact will be much more amplified because of this mixing. So it is known that when VC is contaminated with dust, the radiative effects due to composite aerosol will be significantly larger. And it is also known that VC is contaminated with sulfate, again its radiative voltage is much larger. The VC is a small particle and sulfate can form a small layer over the VC particle. Then we expect that it will be shaded. Sulfate is a transparent material which can coat over the black carbon. So we usually expect that it is shaded from sunlight, so its absorption effect is smaller, but it is not that. There is something called lensing effect. This layer will focus more radiation to the particle, and also it will have multiple reflection from the particle. Whatever is reflected back will interact with that small layer, and it will again get enhanced. So it is a complex scenario. It is not yet solved yet. We are still investigating those aspects. And an issue I would like to discuss is BC aerosol a warming agent. See, it is not only science, it is having a lot of implication to international policy debates. So when there are policy debates, you know that developed countries are under pressure to reduce CO2 emissions. That means they have to compromise a lot. And there is a tendency to project BC as a warming agent. And as I said, its lifetime is very small compared to CO2. So lifetime of BC is about few weeks, maybe 2 to 3 weeks, and CO2 is about 100 to 200 years. So even if you cut down the carbon dioxide concentration completely today, it will take 200 years to get its effect, because whatever is there will remain in the atmosphere. But if you cut down the BC emission assault today, for example, this can be controlled. That is the argument which is made by the developed countries. That it is possible. You put a good filter here, you will be able to stop it. In that case, in about 20 days, you are going to reduce the complete warming due to BC. In Beijing Olympics, Beijing was a highly polluted city, and they shut down all the sources, and within few months they completely cleared the atmosphere, because many countries said that your air pollution was very high. Very similar to I have shown you that picture, pollution control board picture. It was very high, much above healthy standards. So they said, many countries said we will not come. So they have cleared it. So many countries are using it in international policy debates that lifetime is so small, why don't you developing countries like India and China reduce the black carbon. So they argue that fossil fuel black carbon, fossil fuel is coming from automobiles, and biomass burning is also there, have a significantly greater amount of black carbon than scattering organic carbon, making reductions of these sources particularly powerful mitigation strategies. So why, even if we reduce CO2 carbon dioxide by now, there is no use. It will take many hundred years to get its effect, but more effectively reduce the black carbon. So that is one issue. So we needed to study further about that before doing anything. So I want a few statements to make on that. Mitigation of BC aerosol as a quick solution to climate change. See, there are several quick solutions being proposed, so some of them I will try to share with you. Is it a quick solution? See this simple example. You may not understand the complete details of that, but what I am going to show you is that surface reduction due to black carbon is larger than its atmospheric absorption. So that means the cooling of Earth's surface due to black carbon is larger than its absorbed energy. That means absorbed energy is utilized in warming the atmosphere, and this much energy is cooled at the surface. So atmosphere is not only warmed because of direct absorption of the radiation, it is also warmed from below. Surface get heated up, and then the atmosphere get close to the surface will get heated up. In that case, nobody is taking into account this fact that atmosphere, if you clear BC completely, then you are also reducing the cooling from the surface. Effect of that is not accounted in any of these calculations. So surface, this will happen, the surface and atmospheric effect will be same only if BC is completely absorbed. Yes, if you have a BC particle which has only graphite, then it is true. If you reduce the BC, then it will be same. Then also, I am not telling that you will be able to cool the planet. It will be same condition will be maintained. So here, in current scenario, why this is happening is that over Indian region, BC is not completely absorbing. It is scattering also. So part of the scattering is cooling the plant. So you are removing that also, and absorption and scattering is cooling the surface of the air, which again cool the atmosphere. If you are removing, you are removing that cooling effect also. So surface cooling is larger than atmospheric one. So what I am trying to show with this slide here is it will not work. If you remove the PC, it is not going to clean it is not a clean solution. And there are other issues also. See, if you have read the news recently, there were several reports. Black carbon second only to CO2 in climate change. So black carbon is second to climate change. One thing which is forgotten there is that the A is CO2, B is the black carbon effect on warming of the planet. If one student is getting 99 marks out of 100 and second rank holder is having 1 mark, he is still second. But are they comparable? Is the question you have to ask yourself. There are many students, first rank holder got 99 mark out of 100 and second rank holder got 1 mark and everybody else got 0. So will you compare? We will not select the second rank holder if it is IISc case. We will select only the first. This is CO2 and this is black carbon. So here in my own language, the attempt is to artificially amplify the EC climate effect to make it comparable or at least significantly other than the current estimate. So this will come here so that in policy debates they can say that it is kind of comparable, so you reduce it. But as of now it is like this. There is a large difference between the two. That's why I said that such statements you will see from here. These are all very recent reports in this issue. See, burning fuel particles do more damage to climate than thought near time. One knows. And black carbon, larger cause of climate change, previously assessed January 2013. Black carbon, second only to CO2, voice of the wind. And black carbon, a powerful climate pollutant, Reuters, 2013. See, all years you see, it is not 2002 or 2004 I have shown you before. It is all very recent. Black carbon is also global than previously. So, all those things I ignore. This is difficult. That is the International Council for Science Union. They have a scientific body. Black carbon and warming is worse than we thought. So if you read this statement, it is not a simple statement. It will have a lot of international policy implications. And lastly, on that topic, see, black carbon is not emitted alone any time. You see, automobile or biomass burning. If you take biomass burning like this, it is emitted organic carbon and black carbon. So organic carbon is a very strong cooling agent and black carbon is a very strong warming agent. So typically it is considered safe, both cancel each other. So the net effect is cooling only because sulfate is there, organic carbon is there, black carbon is there, and here automobile emission also, black carbon is dominating. Most of these sources also emit scattering aerosols, such as organic carbon, which are cooling agents. Any attempt to mitigate PC would lead to reflection of cooling agents as well. So we need to understand the relative importance of various aerosols, which is warming or cooling before any PC mitigation effect. So that is my view. And again, do we know what is black carbon and what is the definition of black carbon? That is also not known. See, recently, Intergovernmental Panel for Climate Change released an assessment report, Climate Change Assessment Report 5. And there were serious discussions and debates that what is black carbon? Do we know the definition? We don't know the definition, actually. The definition of DC depends on the measurement. You will see many instruments which measure DC in my lab, and you will see that elemental carbon, black carbon, soot, refractory black carbon, and many more. So different instruments gives you different quantities and different units, different measurement techniques. So in that condition, can we make any conclusive statement about what is quantum metals? That is my question to you to think about. So this is the scenario. Nothing much is known about black carbon aerosol and its kinetic. And another issue 4, aerosols and ionization. I have already told you about this. You have a 5-fold increase in aerosol optical temperature, and Prof. study shows that about 23% fraction increase. If you correlate, it will correlate very well. But we do not know whether it is because of this it is getting better or due to some other reason. What I learned from Prof. is that it is not just like just a warm glacier and it will melt. It is not a piece of ice. It is a large amount of ice deposited in that region. I am not an expert on glaciers, but he is here in the first group. He told me that it is a large body of ice, so you need to do mass balance and other calculation before we say whether this much temperature increase can melt it or not, or how much, or how long, what is the response time. Is it 10 years? You need to constantly warm that, or 15 years or 100 years. Those are all not clear. And if you want to know further about whether aerosol can have any effect on glaciers, at least Himalayan glaciers, then you need to answer this question. Can surface aerosol reach higher surface? If so, how? That you have to answer. So I will show you few slides. You can guess whether we can reach what. We have conducted a large number of aircraft campaigns. Indian Space Research Organization is maintaining an aircraft which is instrumented, and from 2006 to 2012 we have made so many aircraft campaigns. You can see that part, aircraft parts. And this is what we have seen. We have seen an elevated aerosol layer at about 3 to 4 kilometers. And more than 70% of the aerosols was found located above clouds during 3 months. Thus, most of the campaigns are during 3 monsoon season. One reason is not because we wanted for a monsoon season, because this aircraft is available during the 3 monsoon season. Because this is not a 24 experiment. This is a survey aircraft. They use it for survey. So when clear sky condition like winter, that aircraft is not available, they will be using it for survey. So we will get when it is relatively cloudy condition, they cannot do survey. They provide us that they are sharing the aircraft. And if you see the vertical profiles of warming coil, you will see that at around 2 to 3 kilometers there is a large frequency measured and observed. Something similar to the DC energy issue I have mentioned before. So this is a region which is not understood well. So above 2 kilometers you have a large discrepancy. There is a tendency to agree close to the surface. So something is happening above 2 kilometers. So anything happening at a higher altitude, you have implications in glaciers, so that you can remove. These are all electron microscope pictures, which shows that very close to the surface, aerosols are existing independent species, and very above 2 to 3 kilometers altitude, they are existing in mixed state. So that means above 3 kilometers, your climate effect or warming effect of aerosol is much larger than expected. It is not, if you calculate using a radiation model, either simple or complex model, you are not going to simulate it back. It is very difficult to simulate it. And to study that further, we have done a major experiment to April 2012, almost a year. And this is Himalayan region, Nainital. This is called Astronomical Observatory, AEROSOL. And you can see the observatory. So we have set up some instruments there to study the aerosol cloud interactions. And it was an Indo-US experiment, joint experiment. And the speciality of this region is that topography is like this. This is surface very Indo-Gangetic basin, is about 200 to 300 meters above mean sea level. And this is about 1950 meters, almost 2 kilometers above mean sea level. And you have a sudden increase. From this digital elevation, you can see that it is a sudden increase in the altitude from the main. So the advantage is this location is a suitable place to study the transport of aerosol from Indo-Gangetic basin to higher levels. That is why we selected that location, and this is the experimental setup. And what we have seen is this is a typical LiDAR. LiDAR is an instrument which you will see in the afternoon, and I will tell in my second part of this presentation also. It is light detection and ranging, where you can probe the atmosphere from surface to some altitudes. And any location you make a LiDAR measure, you will see that in the morning hours the aerosol levels are close to surface of the earth. Then by afternoon, the aerosol levels goes to higher altitudes. The reason is boundary layer dynamics. I don't know, somebody told you about atmospheric boundary layer. But then atmospheric boundary layer can transport, atmospheric boundary layer height is more in the noontime compared to early morning hours. Early morning hours, atmospheric boundary layer is shallow, and if you relate it to the surface warming of the due to solar radiation, it goes up, the height goes up. So along with that, particles also can go to higher levels. So if you take morning to afternoon optical depth, you see the sudden jump is a characteristic feature. Winter, if you take it this side, optical depth is less than 0.1, and summer and 3 months if you take is about 0.5. Very, very high. So where this comes from? It is not because summer and 3 months some activities going on here. This is coming from the surface of the valley. Because boundary layer cannot take the particle in winter because it is very cold. So summer and 3 months because of intense surface warming, AOD can go very high. Because aerosols are coming from surface to 1950 altitude. Particles are, it looks like particles are actually getting transported from surface of the earth to that level. And then using the same aircraft, we have conducted this campaign, and we have found that more than 70% of aerosol was found located above clouds. So I will tell you why I say above clouds or below clouds. If you have a cloud layer below the aerosol layer, clouds present below the elevated aerosol layer act as a highly reflecting background. So it is almost like a mirror. We are keeping a mirror. Clouds are very white. So that means its reflectivity is very high. So it is reflecting large amount of solar radiation back to space. So when you are placing an aerosol layer above a cloud, the absorption effect will be much, much larger. A substantial fraction of aerosols are located above cloud, and part of it is in mixed state black matter that already enhances its absorption character. So the summary is that an enhancement in aerosol induced warming in low cloud as much as a factor of 2 to 3. So that is what is happening. When you take the aerosol to higher levels, you have intense warming above clouds. So you have a cloud layer below, atmospheric layers above the cloud. If cloud layer is 3 kilometers altitude, 3 and above, atmosphere will be warmed because of absorbing aerosol, process of absorbing aerosols. And see the latitudinal changes in the vertical profiles of the aircraft cabin. What is shown here is a cloud, and this is altitude. And this is 4 points which I am showing here. Northern Indian Ocean, most of the aerosols are close to the surface of the air. And you go to the southern coast, it is little higher. And then southern, central India, it is even more. 50 to 70% of the aerosol is above clouds. And central India, north of Hyderabad, most of the aerosols are above clouds. That way you extrapolate. Close to the Indo-Magnetic basin, it is going up like this. We have not done a campaign for that region, close to the Indo-Magnetic basin, because pilots are not that comfortable flying near the Himalayan region. That is a small aircraft. This is pre-monsoon. April, the daytime. Huh? It includes both, because these are all average of many campaigns, many flights, so that it will change, time will change. So morning or afternoon can be. But day and night both we have done measurements. And if you take this extrapolate this to Indo-Magnetic basin, it can go to very high altitude. This is already 4 kilometers close to the central India. And if you extrapolate, it can go to 6-7 kilometers in Indo-Magnetic basin. That is where the glaciers are. So that is one indication. You can't tell anything. I'm not telling that if aerosols can reach the glacier altitude also, it can affect. It is true that it can warm the atmosphere at that altitude, but again, as I said, simply warming the atmosphere, is it sufficient to melt the glacier is a question which is to be understood. It is not like a simple like we warm it and it will melt. It's not like that. But there is a possibility that aerosol from the surface of the, close to the surface of the earth can get transported to glacier levels due to various atmospheric processes. There is a possibility. That is all we can say as of now. And here is the summary of aircraft campaign. Here you can see that 10 to 30% of aerosols are above cloud level. Here 50 to 70% of aerosols are above cloud. And this can lead to 2 to 4 degree Kelvin, again day and night average. And surface cooling of 1 to 2 degree Kelvin. So you have a surface cooling simultaneously with atmospheric warming. Surface reaching variation is reduced by as much as 50 watts per meter square. So I can tell you it is about 342 watts per meter square at the surface if you remove all the species. So out of 342, 50 is a large number. And here it is 20 parts per meter square. So this much particles are at 5 to 7 kilometer level, almost 50 to 70%. So that can contribute to 2 to 4 degree Kelvin. That is a large warming which can happen over that region. And the consequences are the Himalayas contain the largest store of water outside the polar ice cap, and 7 great Asian rivers depending on that. 2 billion people in the river basin depend on Himalayan glaciers for their water supply. And rapid melting of Himalayan glaciers will first increase the volume of water in rivers, causing widespread flooding, and then hundreds of millions of people floodplains, highly vulnerable to raised water levels. and that will impact on water supply later. Once it is melted completely, then first floods and then impact on water supply. Water supply will be affected. So this is what in 2050 or 2100 scenario, one possible scenario. But again, I cannot say anything conclusively because these are only indications. Not much is studied in detail. It is all in very preliminary stages. So in the next few years, you will get a much more clear picture about all these things. But I just want to show you some of the outstanding issues on this topic. And another issue is impact of aerosol on Asian inferences I have told you in the morning. And one study said that absorption of solar radiation and consequent warming by aerosol over Tibetan valley act as an elevator which draws in warm and moist air over the Indian water leading to advancement and subsequent intensification of Indian summer monsoon. So he is saying that aerosol increase the monsoon rainfall. And another study said that large reduction of solar radiation at the surface simultaneously with lower atmospheric warming increase the atmospheric stability, slow down hydrological cycle, and reduce the rainfall during the monsoon. So there are so many studies on the impact of aerosol on Asian monsoon, and many studies are contradicting each other. I have seen studies saying that presence of aerosol intensify tropical cyclones, and I have also seen studies saying that it is reducing the intensity of tropical cyclone. So, which one to believe and why such contradicting statements are made? That is one thing which you have to think. I will give you some clues. Most of the models which I have shown, also 99% of the models which they use chemistry transport model simulations as their input for aerosol. Because if you want to incorporate aerosol on a global scale, you don't have measurements. It is an emerging field. You don't have adequate measurements. So they have something called chemistry transport model where you describe emission and then you get the aerosol distribution over the globe or on a regional scale. And this is one fact. When we compare the chemistry transport model output with the measurements, it doesn't match. Again, it is 2 to 6, almost a factor of 2 to 6. So at least over Indian transport model simulations of aerosol are unrealistic and lower by several factors. Some models are underestimating and some models are overestimating. So with an information which is it is different, it is different than real values. How can we expect that model can simulate accurate picture of climate effect of aerosol? That is my question. You can't simulate the actual picture by using an unrealistic value for that. That is one thing. And another last issue I want to discuss with you is can aerosol from lower troposphere reach stratosphere? There was an attempt to study this by making BC using high altitude resolution using AFR facility in Hyderabad. And if you see that this instrument was sent into the higher altitudes, and we have seen large amount of black carbon in 2 different layers, 4 kilometers and about 8 kilometers. See, this value is very high. 10 microgram per meter cube is much larger than Bangalore values. So we don't know why this is happening and this is happening. Even this 2 to 4 is comparable to whatever we measure at the surface of Bangalore measurements. In rooftop, we are measuring about 2 to 4 microgram per meter cube. So we are observing that around 8 kilometer altitude. So we don't know how it can be aircraft emissions because if there is an airplane going in that level, it can emit large amount of black carbon. That is one possibility. But anyway, there is a hypothesis that a process known as solar escalator, which can take the particle from surface of the Earth to higher altitudes. See this thing, biomass of burning over Australia. Smoke plumes from Australia was located at altitude between 15 to 20 kilometers. This is a space-borne LiDAR, which shows that these are all aerosol plumes, which is coming from the surface. And they have done, it's an European group, they have done back trajectory analysis, and then they tracked the plume. It is possible, many things are possible in current era. They can trace the plume and locate the source, where it is coming from. If you observe some phenomena here, you can trace back where the plume is coming from. So then they have found that it is going like this, like a staircase. So they call it a solar escalator. This is happening because first the biomass burning aerosol get higher because of the warming of the fire itself, and then it warms the atmospheric layer which is present, and then when the atmosphere is hot air rises and BC particles are so small, so along with that air, BC particle also goes up, and then it won't come back because incidence time is large, it stays there, and then again it starts warming the atmospheric layer and it goes up again. So it's old. So some people call it a self-lifting of black carbon, and some people call it a solar escalator. And this is the altitude at which it was located. The different moves from 9 to 18 kilometers. 18 kilometers is very close to stratospheric altitude. So by its own, this study shows that particles get from biomass burning or any other emission. If it is absorbing type and small, it can reach to that level. So, so what? See, if particles are reaching the atmosphere, we are all living near the surface of the Earth. So what is the issue? Consequences of black carbon in the atmosphere. One thing is, you will have an intense warming of atmosphere due to black carbon, because this is the equation for warming rate. If you have the same aerosol layer near the surface, assume that you need to 0.5 degree Kelvin per day warming for a given property, and you are taking this same aerosol layer to 20 kilometer altitude with the same property, it can warm the atmosphere almost 12 Kelvin per day. So that is what you see from this equation. You calculate into this equation, you will see that it is very, very high. The reason is atmosphere is dense close to the Earth's surface and thin at higher levels. For a given absorbed energy, warming is much higher levels, because absorption is same. Here, because the aerosol properties are same, amount is same. Here also aerosol properties are same, amount is same. But the difference is, for a given absorbed energy, the consequent warming will be very, very high. See, it is very clear from this. Delta F is same, but delta P, that is pressure difference between two layers, is different here. Because of that, warming is very high. So, if BC is present in the stratospheric altitudes, even a very, very small amount, what I have shown you is something comparable to that observed over a metro city. So it is not a small amount, it is a substantially large amount which is reaching the free tropospheric altitudes. So you can guess how much it can warm. It will be much larger than the expected. And now, with that background, I will tell you the consequences of BC in the stratospheric altitude. This is from literature. If you do a literature survey, you can see that aerosols are shown to interact with the gaseous environmental chemicals. And one potentially important reaction is ozone decomposition on black matter. We know that ozone layer is located in the stratospheric altitudes. So it is a very important thing, and some people were given Nobel Prize for finding ozone destructing chemicals in '95. And because of that, now so many controls are in place, and stratospheric ozone hole is now in the process of recovery. In the next few decades, it is expected to be normal. So that is the current situation. So in that condition, if we are injecting large amount of aerosol into the stratosphere, aerosol can provide large surface area available for heterogeneous groups in the upper troposphere and lower stratosphere. And rate of reaction depends on the surface properties. And we see some of the electron microscope pictures I have shown, you have probably seen that it is hollow. Some particles are like hollow and some particles are like sponge. So they can provide a large surface area for heterogeneous chemical reactions. So that means it is very dangerous species for as far as ozone layer is concerned. And aerosol provides surface area on which chlorine gas in cold or atmosphere can cause reactions that intensify destruction of ozone. Though aerosol is not directly destroyed, it acts as a neutral body. Some chemical reactions need a neutral surface for reaction to happen. And aircraft-based measurements revealed that several episodes of anti-correlation between ozone concentration and aerosol surface area. And many more. We will get many more if you search. And all this shows that it is not good to have aerosol in the stratospheric altitudes. And also, some of these reactions are temperature dependent, have a positive temperature dependence. So because of that, if you are going to warm that stratospheric altitude by 10 to 12 degree Kelvin per day, that is a huge warming, and simultaneously provide the surface area for heterogeneous chemistry, it is kind of very much possible that it can destroy ozone.
In lower troposphere, the black carbon affect mixing ratio.
Yeah, it is same applicable both in lower troposphere and stratosphere also. I have seen several people presenting papers which shows anti-correlation between ozone and other species. And one thing to remember here is that whatever reactions I have told you, all these studies are conducted in laboratories, not at stratospheric altitude. It is not easy to go there and do experiments. And because aircraft cannot fly at 25 kilometer altitude, and very, very less number of planes can go to 20 and specially designed and are not performed under the same conditions found in upper troposphere, lower troposphere. I mean temperature and pressure conditions. Chemical reactions very much depend on this temperature and pressure conditions. And temperature plays an important role in the processes, and in presence of aerosol reduces ozone. And it is difficult to simulate such temperature conditions observed in DTLS in a laboratory setting. It is not easy. And reaction probabilities that were determined under typical laboratory conditions may differ substantially from actual reaction probabilities under real atmospheric conditions existing at stratospheric levels. And finally, only a small fraction of aerosol may reach stratospheric levels. It may not be feasible that a large amount of aerosol can reach stratospheric altitude. Because what I have shown you is only 8 kilometers and 4 kilometers. Further, Australian forest fire study showed up to 18 kilometers, but still no one has shown 25 kilometers. So it is still a hypothesis, it is not yet concluded. So it is an outstanding scientific problem. And then another aspect I would like to share with you is what we learned from volcanic eruptions. See, one thing we have learned from volcanic eruptions, when you have volcanic eruption, it injects large amount of aerosol in stratospheric altitudes. And this is El Chichon and Pinatubo, two major volcanic eruptions, reduces the surface solar radiation and cooled the Earth atmospheric system by 2 to 3 degrees. So, following any major volcanic eruption, you have a reduction of temperature. So, did you learn anything from that? So that made some people think that why don't we inject artificially aerosol in the stratosphere and cool the planet? So that is what we learned. Why cannot humans inject like this and then cool the planet? See one volcanic eruption. This is an volcanic eruption here, and this is how its plumes are going. It is injected into the stratosphere. So this can fill the entire globe in a matter of few months. So that also indicates that if you are injecting aerosol in the stratosphere, you don't have to really inject all over the globe. You inject it from one point. Enough. The circulation pattern will take care of the rest. So the entire globe will be in stratospheric altitudes, not the surface level. It will be filled with aerosol once you inject it in the stratosphere. So you send it in rockets from really good. You go to stratospheric altitude, inject it there, it will go everywhere. So same thing with any other location. So it is called Earth system engineering. So this equation is the energy balance equation of the Earth atmosphere. You probably have seen this equation many times. Even though you have not seen, I will tell you what it is. It is incoming radiation and this is outgoing radiation. So here you have a zero solar constant, reflectance of the Earth's atmospheric system, and this is sigma T. T is the Earth's temperature, effective radiating temperature. So incoming radiation is equal to outgoing radiation. That is the balance. So here, by injecting large amount of aerosol in the stratospheric altitudes, either using a set of aircrafts or rockets or high altitude balloon. So here what you are trying to reduce is, you are trying to reduce the incoming solar radiation. You are trying to block the radiation at stratospheric altitude. So this alpha will be more, reflectance of the planet will be more. So reflectance is more means less radiation reach the surface of the Earth. And then another option is put a large mirror in space. This is the mirror in space, and here your undertaking is to reduce S0 by a percentage, a small percentage. Both are same, whether you increase the reflectance of the planet or reduce S0, having a similar result. And then the final aim is to cool the planet. But like that, so many methods are there. Probably somebody may have told you already. Not you just search Earth system engineering, you will see all the methods. See, this is some concern which I have. One is global acceptance of this method. Russia is so cold and USA is cold and moderate temperature. And they say that they want more cooling. Russia prefers more warming. Then there will be no consensus. Nobody can do it. It has to be done internationally. Because if you inject at one location also, it is affecting the globe, not at one location. And there are environmental issues like acid rain. You are injecting sulfate aerosol, which is cooling agent, and that finally will come down. It will not stay there. It will slowly come down and pass sulfuric acid. So the acid rain and effect of monsoon. I already told you that if at all you are shading the solar radiation reaching the surface, you are shading both land and ocean. So land responds much faster because of less heat capacity, and ocean responds slower. So in that case, you are effectively reducing the contrast between land and ocean. So that can affect monsoon circulation, onset, and many more. There are several other effects. So to summarize the scientific part, my view is that crucial question to be answered to tackle climate change are so many compared to what is known as on today. And as we study, my experience for the last 20 years, I have studied aerosol. My experience is that as we study aerosol climate problem more and attempt to answer crucial questions, it appears that picture gets even more complex. That is my own experience based on last 20 years of my research. With that, I will stop the scientific presentation and I will try to help you with some of the aerosol measurements so that it will be useful for you to see the lab and ask questions. And if you have any questions related to that, I will be happy to answer because you may forget after this another 20 minutes I will take for this presentation.
So do you see any decrease in ozone in the intergalactic plane?
Because it is stratospheric thing, I would like to consider it as a global problem than only Indo-Gangetic Basin, because it is stratospheric layer is in the ozone layer is in the stratospheric altitudes. So it is very difficult to say over Indo-Gangetic Basin whether any effect is there or not. If at all effect is there for the whole globe. So it is a kind of global problem. Stratosphere is well mixed region. So at one particular place it is very difficult to isolate.
So you were telling the doubling of aerosol by percent over here. This is based on observed data or it is expected that
Observed data. I have shown is a measurement data which is available from ISRO. Last 20 years data is there, so it is showing an increasing trend at the rate of 2.4% per year. So if you extrapolate that way, assuming that government is not doing anything to reduce aerosol emissions, then it would reach that level. By assuming that by 2020 government is taking strict action, that it may stabilize and even come down. So it is a prediction based on past 20 years. If past 20 years government did not do anything, I don't expect next 30 years also they may not do anything.
similar trend is assumed in climate models also for projection.
No, as far as I know, nobody has used it. People who are doing climate modeling studies, they can use that and predict what would be the climate conditions in that scenario. There is an opportunity. Because these are all new results. You have seen 2013. It's published in 2013, only a few months back.
So you have told that it is the black carbon and the cloud look different. And there will be net effect on water. But scatter aerosol, there will be some cooling and precipitation. But if only we assume the warming due to the black carbon, not due to the greenhouse gas, then it will evaporate either we have considered both greenhouse gas effect plus black carbon effect.
What I have shown is only due to black carbon. only warming due to black carbon alone is sufficient to evaporate clouds. So if you include greenhouse warming also, it will be even more.
But in that scattering case, there will also the greenhouse effect.
No, greenhouse effect is in infrared region. So scattering effects are not that dominant.
Well, those clouds, when people they form due to those aerosols and due to the greenhouse effect, that it may evaporate.
Only greenhouse effect it may be difficult. But if you take the two together or only BC, that is because I have not seen anywhere greenhouse effect evaporate clouds.
Is there an effect of aerosols on microwave emission from our?
It can, but they are so small. Microwave is, I mean, when you compare the wavelength and size, how much extinction it can exert to that it is. But large dust particles are known to have effect on microwave radiation. Your particle size should be very large. Infrared region, for example, 8 to 12 micrometer window, there is a strong influence of dust on that radiation. Microwave is even longer. So it may not be that efficient, but still there will be some effect if you have very large dust, for example.
So the aircraft project you are doing is a very interesting project. So do you characterize aerosol?
We collect aerosol also.
So which one has the concentration of black carbon or organic carbon?
All. We take chemical samples, we collect black carbon, we measure scattering coefficient, absorption coefficient,
No,
size.
Which has got most concentration in Indo-Gangetic? Organic carbon or black carbon? Is there any?
Indo-Gangetic basin, it is more, you can say 50-50. Both are there, and depending on the season, it varies. If you take winter, you will have one ratio. In summer, you will have another ratio.
That's also, I mean, if you see the seasonal cycle, when there is virus residue burning in the Indo-Gangetic state after this crop season.
Yes.
So, I mean, at that time,
Organic carbon will dominate. Yes. So that is a cooling agent.
So it would be very interesting to see some of the applications like that. No?
Yeah, Indo-Gangetic basin, actually there were some aircraft campaigns made during last winter, but we have not analyzed the data yet. Yeah. If you have any other question, you can talk to me in lunch time or any other, or email me if you have a question after leaving this course. I will tell a few minutes about this instrumentation, what you are going to see in the lab. As I said, the batch of 10 will go to the lab. I will tell the names, every batch. And then other people will do the tutorial here. So we will meet at 2, and then 10 people will go to the lab. My students and project staff will be there, and rest will be here. I will give you the tutorial. And this is a measurement system, typical measurement system. So you want to measure a physical phenomenon, and you need to convert that into electrical signals. So that is called a transducer. And then you have a data acquisition system and computer to store the data, selected data. So it can be direct measurements. We call it as in situ, or it can be remote sensing. And remote sensing can be active and passive. Remote sensing is not only satellite remote sensing, it can be ground-based also. There are different ways to do ground-based remote sensing. And this is one typical example of a high volume sampler. What you are doing here is use a pump and take air samples through the sealant, and you have a filter paper, and the air molecule will pass through that filter, and you will get aerosol particle deposited on the filter paper. You know the weight of that little paper before experiment and you weigh it again. So the difference between the two will give you the total mass of particles, and you know how much air is sampled. So that much air, you have this much particles in the atmosphere. That is the microgram per meter cube of air. I have shown you that is how it is measured. And this is high volume sample. And in some cases, multi-stage impact is placed in the air stream, where particles of different sizes are collected at different layers. And then you can get size distribution of particles. But nowadays this is not done because you can do it better way optically. You illuminate the sample with a laser beam and then you measure the scattered light. Then you can get this information in a more efficient and accurate way. And this is a particle counter. It's called the condensation particle counter. But you are doing in this experiment, in this instrument, is the take sample inside of this, and you have a chamber which is saturated with either water vapor or alcohol vapor. Methyl alcohol is contained and is saturated. So when the particles are passing through that medium, you get size will get increased because of condensation of vapor. And then a laser beam is used to illuminate these particles. And from the total scattering, you can measure it with a detector. From the total scattered light, you can infer the total number of particles. And it can count. It can tell you 120 particles per centimeter cube or 10,000 particles per centimeter cube. So depending on the concentration, you will get the concentration. Yeah, one number you will get irrespective of the size. And this is how it works. You have an aerosol inlet and you have a saturator where the particles are grown to larger sizes. You have a laser beam illuminating these particles and then detector. So detector output is at constant, this calibration for whatever is measured here. And aerosol outlet, particles will go out of the instrument to the aerosol outlet. And that can give you the total number of particles per centimeter cube of the atmosphere. And here, this instrument can give you, it is called a scanning oblique particle sizer, where you can get the size distribution. As I said, you don't have to use impactors because particle loss and not the impactor is very, very high. So, what this instrument can give you is an optical way of getting the size distribution. So here, an electrostatic classifier uses an electrical mobility detection. During the operation, aerosol sample first passes through a single stage impactor and then it is charged. When particle is charged and when you apply an electric field, the trajectory of the charged particle takes a circular path. Because you have particles which are charged and it is passing through a electric medium, electric field. So it takes a circular path and particle with only a narrow range of electrical mobility pass through the field. And electrical mobility is inversely proportional to particle size. So you change the voltage applied in regular steps to increase or decrease the electric field strength. You will be able to control the trajectory of the particle. So like that, you can electrostatically separate the particles into different sizes. This is a simple example how it is. This is electrostatic classifier and aerosol inlet. This is electric field and it goes. So this particle will not come out. This stream will not come out. Only particles which this trajectory will come out of the inlet. That will be corresponding to some particular size, depending on the applied electric field. So you change the electric field, this will come here, this will go down. You change it different way, this will come here, this will go here. So like that you can adjust the electric field and control the trajectory of the particle and measure that. And then outlet here, you will have a counter, same instrument. See, the counter is still there. This is a particle counter. It is some part of water or methane alcohol. So whatever is coming out of this classifier will again go to this particle counter, and that can be counted here. And the output will be like this. Number of particles as a function of radius. So here you can see two modes. This is called a bimodal distribution of aerosol. So like this you know how much particles are there in each size of it. And remote sensing, you can have ground-based and satellite-based remote sensing. What you are going to see in the afternoon is a ground-based remote sensing, the sun photometer. But it is a technique for measuring or observing, monitoring a process without physically interfering with the system. If you look at a tree or you are feeding heat from a kettle, it is all remote sensing. You are remotely sensing the object. Optical telescope, camera, radio telescope, all are examples of various remote sensing instruments. It can be active or passive. The difference is active remote sensing techniques, you have one source of energy. Passive remote sensing, you will be using sunlight. So radar is an example of active remote sensing. And here radiation reflected by the medium is received back, and properties of the medium are obtained by applying principles of scattering theory. And passive remote sensing, they do not use an energy source, and satellite remote sensing and all are part of passive remote sensing techniques. And satellites measure solar radiation coming from the surface, coming from the earth and the atmosphere. And over land, satellite remote sensing is more complicated. So ground-based remote sensing is more accurate. And it has the following advantages over direct measurements. The sensor need not be in contact with the substance under observation. In direct measurements, you are actually disturbing the system. You are taking the sample and processing it. You are disturbing the system. Here, it is measuring a process without a disturbance. And probe large volumes quickly. That is absorbed. And remote sensing can be ground-based and space-borne. But we are going to discuss in the afternoon. The lab is ground-based remote sensing. And this is one instrument which can do ground-based remote sensing. It is called the sun photometer. And principle is very simple. I already told you Lambert law. I is equal to I0 exponential minus extinction coefficient. If you take the actual atmosphere, it is minus optical dust into m. If it is sun is in the over atmosphere, m is equal to 1. So you simply measure the output voltage from a photometer, take natural log, get a straight line, equation for a straight line. The slope m and y equals the E0. And from this slope is the optical depth. You get the optical depth from the instrument. You don't have time to analyze the data, but at least you can see the instrument and its operation. This is how you get a straight line. And it is a combination of molecules and aerosol, and molecular optical depth is well known. You can easily get aerosol optical depth from this. And satellite remote sensing is the you have a sun satellite geometry here, and whatever is coming to this satellite sensor is coming from both atmosphere and surface. That we are not covering in this course. And then another instrument will study the vertical distribution of aerosol from ground, is micropulse data, where you have a telescope and a laser beam. A laser is sent into the atmosphere, and you can get the reflected energy. This is how a radar in operation. This is from the rooftop. You are sending a laser beam and receiving the scattered light back. And then you will get aerosol properties from surface to up to about 30 kilometers altitude, depending on the ability of the LiDAR. And it is simple. An electromagnetic signal is recorded by a detector after it interacts with a target. And the signal is a function of target. And what you want to know is target property. And then it is a F inverse test. So it's an inverse problem, inverse mathematical problem. You have to solve it. It is not that difficult. And LiDAR is the optical analog of radar. Simply, instead of radio, it is light. You are using a laser beam instead of microwave. And they are active remote sensing techniques because they use the light source, laser source. And then measurement is depending on that. And this is a LiDAR system, light detection and ranging. And see, this is a laser beam, and this is a telescope. This can measure the return energy. You send a pulse and receive the return energy. You see, this is a laser pulse source provide a range distance information, and then the pulse is interacting with the atmosphere. And if you see here, this is how it works. See, a laser pulse is sent, it interacts, and signal is received by this telescope, and finally it goes to the data acquisition system. So simple, it is very simple. Typical block diagram of a LiDAR is like this. You have a laser beam and a telescope to perceive the. This is atmospheric standards, and you have a data acquisition. And you have many applications. You have military applications, civilian applications, commercial applications. What we are using is for environmental applications. And this is the same block diagram. This is how you get the distance. See, the total time it is take the beam, the pulse, laser pulse take to go from up and down. It's time up plus time down is equal to total distance velocity of light. So you can calculate the range C into total impedance. So this clearly explains how you get the altitude information, from where the pulse is coming back. That is, by knowing the velocity of light, you can calculate it. So like that, it is called time gauging. This method is called time gauging. By gauging the time, you can get information up to the entire altitude with the understanding. This is LiDAR equation which is to be used for getting the information. You don't have to remember this. I'm just showing the complexity of the analysis. It is not simple. So many parameters are there, and you can see the number of parameters required, starting from the atmospheric transmission, receiver efficiency, propagation rate, and effective basket cross section. A large number of information is needed, and this is the block diagram showing how it works. Atmospheric backscatter will be used as input in scattering theory, and then you can calculate the total atmospheric extinction coefficient, and that is sum of these two, aerosol and molecule. And molecular extinction coefficient is well known for any wavelength. You can calculate. Rayleigh theory is known, and you subtract it, you will get the aerosol. And this is a typical mechanical design of the LiDAR. And actually, it looks like this, very complex. And finally, I just want to show you this concept of the liquid mirror. Nowadays, in LiDARs, the mirrors are not used. Glass mirrors are not used. So nowadays, it is used liquid mirror. Because if you want to probe 100 kilometers, you need to use a huge, almost 20-meter diameter mirror. That it is very difficult to maintain, very easy to break. You move slightly, that mirror can break. So what you do is take a container and fill mercury. Mercury has very high reflectance. It's almost like a mirror. And then rotate this drop. You rotate it, the mercury will form a concave mirror depending on the speed. If you rotate fast, your focal length will change. And if you rotate slowly, this will form a small, slightly curved surface. That can be used as a mirror. So this is called liquid mirror. And future what is to be done in this direction is satellites. If you can use different satellites together, you will get a surface, because surface measurements are well known and so many measurements are already available. What we don't have is satellite measurements. So right now what we need to do is to use several satellites together. That multi-satellite analysis provides an opportunity to try information about aerosol. But first thing is everything is available in one satellite. It is possible actually if you use the information intelligently. See here one example I can show you. This is a reflection from water. You can't see what is below the water. You just take a polarizer and rotate it to its axis. Then you can see, because what you are doing here is you are filtering out all the reflected energy from that. So because of that you can see what is below. So similarly, if you use similar techniques, you can actually design utilizing a combination of features used in a satellite into one. This is a satellite sensor we have developed at our own lab. It is not there, it has gone to ISRO for modification. We are not able to show you today, but otherwise this is one small sensor we have developed, and this is the output. That sensor was used at the top of the building. This is how the sensor sees the backwards. And with and without polarization. So here, because of so much information, you are not able to see the atmosphere because it is mostly dominated by the land surface properties. So when you use a polarizer, see it is like night. Your land surface properties are suppressed completely, and you can very well get atmospheric information from this. It is almost impossible to get atmospheric information from this because these are all reflections from things. But in this case, it is like ocean, uniform and not much noise is there. Okay. So major advantages is this, and this is expected to be a very good sensor for future. Thank you. We'll see it. Any question on this topic?
Previous talk. You have shown showing the black carbon or the
Yes. Actually, there are both reports. Some people are saying it intensified, and some other studies are saying that it is reducing the intensity.
There is no answer.
No. As I said, it is all chemistry transport model outputs, and I showed you it is a factor of 3 to 7 different compared to measurements. So I don't believe any of those studies. So we are very much in early stages. Much more has to be done.
What is the mechanism?
You need to improve the emission inventories in the model because most of these models are coming from foreign. So they only worry about their region. They are not bothered about the Asian conditions.
Now, how is higher factor? Which way it is simulating?
There should be effort from our side to improve the emission inventory because nobody else will do for us. Our region, we have to calculate our own emission inventory. Which data? LiDAR. LiDAR is you can operate from anywhere. No. In rainy season and all you cannot operate. And intense sunlight you need a container, air conditioned weatherproof container. So we will have a quartz glass over the container, and that glass laser will be sent through that glass. 1 kilometer. 1 kilometer. There are no other questions. We will meet at 2. Thank you.